Oke.
Kalau saya Zahra, Bapak Kaprodi dari TI Unisa.
Iya, Puan Zahra.
Kemudian nih, yaitu Bu Hapsari ada Dekdin from Science and Technology Faculty.
Assalamualaikum,
Bu.
Prof. Datuk.
Waalaikumsalam, Ibu.
Iya, jumpa pertama kali ini ya, Prof. Mohon maaf,
Iya,
Prof. Iya.
Iya, saya ke Jakarta sudah banyak kali itu, tapi masih tak jumpa lagi kamu. Jumpa Aisyah saja.
Oh iya, iya baik Prof. Besok kalau sudah bisa ke Yogyakarta, boleh mampir ke Unisa, Prof.
Insya Allah, insya Allah. Insya Allah. Pukul jam berapa anak-anak akan join kita?
Ini sudah join,
Ini
Prof. Sebagian.
Sudah join ya?
Ya, kita ada 70-an. Bisa dimulai saja, Pak Ari?
Oke, bisa boleh saya mulai ya, Prof?
Iya, Pak.
Ya, bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Good morning, everyone. Okay, first of all, let us pray and praise to Allah Subhanahu wa Ta'ala because of His bless and mercy, so we can come together without any obstacle in this spiritual room with healthy condition, and we will be able to join webinar of robotics in Industry 4.0.
Amin.
Second, let us greet and pray to our beloved Prophet Muhammad Sallallahu Alaihi Wasallam, who had brought us to the path of light and left the darkness in our life. The Honorable Professor Dato Dr. Abu bin Abdullah as the keynote speaker in our webinar, the Honorable Mrs. Hapsari Wahyuningsih as the Dean of Science and Technology Faculty, Universitas Aisyah Yogyakarta, the Honorable Mrs. Zahra Arwanan Dias as Chairwoman of Information Technology Department, Universitas Aisyah Yogyakarta, my beloved friend, the lecturers of Information Technology Department, Universitas Aisyah Yogyakarta, and all beloved webinar guests. Before we move our agendas, please allow me to introduce myself. My name is Arizona Fridonsyah. I'm one of the lecturers from Information Technology Department, Faculty of Science and Technology, Universitas Aisyah Yogyakarta. And I will be the master of ceremony and moderator for our webinar today. Ladies and gentlemen, on this nice occasion, please allow me to deliver the structure of the event today as follows. The first agenda will be the opening session, followed by the speech from Mrs. Hapsari Wahyuningsih as the Dean of Science and Technology Faculty. And the third is the main event, the general lecture, which will be delivered by Professor Dato Dr. Abu bin Abdullah. And the first agenda is the question and answer session, followed by photo session and closing. Ladies and gentlemen, now we come to the first agenda. Let's open this event by saying Basmalah together. Bismillahirrahmanirrahim. Thank you very much. Now we invite Mrs. Hapsari Wahyuningsih, the Dean of Science and Technology Faculty, to give the welcome speech. To Mrs. Hapsari Wahyuningsih, the time is yours.
Ya, terima kasih Pak Arizona. Thank you for the time. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Selamat pagi, Prof. Datuk. Mohon izin speech sekejap untuk teman-teman mahasiswa. Bismillahirrahmanirrahim. First of all, let us praise and thank the presence of Allah Almighty more for the abundance of grace and the joy of all of us can still gather in this place without any barriers at all and in good health. Not forgetting salawat serta salam we pour out to the Prophet Muhammad. May we all get intercession on the end. Amin, amin ya robbal alamin. First of all, I would like to thank you, Prof. Datuk Dr. Abu bin Abdullah, as a CEO of KWS Business School Malaysia, being willing to fill a public lecture with the theme Robotic in Industry 4.0 today. I'm sorry, Prof, if there is a misspelling of the name. Let me introduce about Information Technology Study Program. The Information Technology Study Program is currently in its 4 years and has just graduated this year's first batch. But in the third year, this study program has received accreditation from the National Accreditation for Higher Education in Indonesia. And then this public lecturer is held regularly by this program with an up-to-date theme to boost student knowledge directly from experts in their fields. And for the participant today, Prof, there are students of the study program and of course the academic community of Unisa Yogyakarta, as well as the general public from outside of Unisa Yogyakarta. We all know that in recent years, humanoid robots have emerged in various countries. Among them, like in Hong Kong, there is a Sophia robot. And then in China, Jia robot, and also in Japan, there is Erika robot, Asteroid robot, and Asuna robot. They are made to help facilitate human work in the world of service. The same is also applied in Indonesia also. Various robot technologies were also developed and assisted in many benefits. Robotic in the Industry 4.0 is closely related to artificial intelligence, and robots are used to help humans. Even in this IoT era, robots even have capability that exceed human in the field of data processing and especially work resilience. By learning directly from the expert, Prof. Dato, today Prof. Dato will add knowledge to general lecture participants, especially related to robotic in Industry 4.0. In the end, I just want to say let's enjoy attending the general lecture until it is finished, and I hope it will running smoothly. Kurang dan lebihnya saya mohon maaf, Prof. Dato. Wassalamualaikum warahmatullahi wabarakatuh. Back to Pak Ari as a moderator. Thank you.
Okay, this is the speech delivered by Mrs. Sapsari Wahyuningsih. Terima kasih, Bu Sapsari. Thank you for Mrs. Sapsari Wahyuningsih for the outstanding speech, and we do hope that this speech will boost our spirit and give us more inspiration, and also give us more insight of this outstanding occasion. Okay, ladies and gentlemen, now we come into the main point, the webinar titled Robotics in Industry 4.0, which will be delivered by Professor Dato Dr. Abu bin Abdullah with Mr. Sadr Lutfi Mufreni as the operator. But before we begin, please allow me to give a brief information about our outstanding keynote speaker. Professor Dato Dr. Abu bin Abdullah, born in Malacca on March 9, 1961, is a lecturer from University Technical Malaysia, Malacca. Impressively, after completing his Bachelor of Science in Production Engineering at Birmingham University, UK, Prof. Abu pursued a postgraduate certificate of education or PGCE locally at Kuala Lumpur. Prof. Abu reflected a keen interest in education and obtaining Master of Science in Manufacturing System Engineering at 1991, and consecutively successfully secured his doctorate in manufacturing engineering in 1996, both at Warwick University, UK. Prof. Abu joined KYS Business School or KYSB in early 2020 with more than 35 years of diverse experience, spanning from the education to management. Prof. Abu was appointed Chief Executive or CE of KYSB on March 10, 2020. That concludes the brief information of our keynote speaker. Now, without any hesitation and waste of time, let the main agenda begins. To Professor Dato Dr. Abu bin Abdullah, the time is yours. Thank you very much.
Nge-freeze apa ya?
Kayaknya terlempar.
Iya.
Apa sambil ditunggu.
Oke, mungkin Prof. Sinyalnya ya atau?
Iya, mungkin Pak Sadul bisa share screen dulu Pak, dicek share screen-nya.
Ari, can
Yeah,
you hear
Prof.
me?
Yeah, clearly.
Clearly, Prof.
Very clear, Prof.
The connection
Okay.
is not that stable.
Oh, yeah.
Okay. Can I start now?
Yes, Prof. Please, we can start now. And I'm sorry
Right.
for the...
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam
Kepada
warahmatullahi
Pak Ari,
wabarakatuh.
moderator, kepada Ibu Dekan dan Ibu-ibu mahasiswa dan dosen-dosen serta lecturer di IT Faculty UNISA. So Alhamdulillah, with the permission and the allowable from Allah SWT that we are now able to have our Zoom meeting webinar on the topic of robotics in Industry 4.0. Actually,
Excuse me, Prof. I think
I think
yeah.
We have some connection problem here. It's not very stable. The internet is not that stable.
Yes, or
Can
maybe
you hear me?
yeah, we can hear you clearly, but sometimes the voice is unstable, Prof. Or maybe if you don't mind, this is just a suggestion for me. Pardon me if I'm not politely asking, but maybe we can do it in off-cam first. Maybe sometimes the when we do it on cam, the signal is not very stable, Prof. Hello.
Ari, I think the connection is not stable. Can you hear me now?
Yes, we can hear you clearly, Prof. Hello?
The connection is not stable. It's
Yeah.
sometimes on and off.
Yes, sometimes the voice is, we can hear you clearly, but sometimes the voice is off. Or maybe we can do it off cam, Prof. Hopefully that without the picture on camera, the bandwidth will, yeah, maybe we can
can
off cam.
help the stable in the connection.
Yes. Maybe the connection stability will increase, Prof, if we do it off cam. Hello, Prof. Hello, Prof. Cek, cek.
Can you hear me again? Hello.
Yes, Prof. Hello. Hello. Okay.
It's so unstable. I don't know, is it my side or on your side? I don't know, but okay.
I
If
think this is clearly now, clearly stable now, Prof. We don't know which side it is, but I think the connection is become more stable now.
okay.
So we can begin
Right.
the webinar, I think.
Okay, inshallah. Right.
Yeah, inshallah.
Let me start robotics industry 4.0, and my presentation will consist about 9 parts. The first part, I try to give some information what is actually IR 4.0. I think most of you might have known that, but just a revision, just to catch up with what is industry IR 4.0, just a few slides. Then part 2, I will give some definition robots as a whole. What do you mean by robots that we might know today? Then part 3 is some history of robotics. Then part 4, some robot anatomy, what is the parts of the robots, and the types of industrial robots, things like that. Then part 5 will be some industry application for the industrial robots. Part 6 will be what are the programming that we used for the industrial robots. Part 7, some safety implementation. Part 8 will be some other application apart from industrial robots. Where can we apply robots actually in industry? Then I will end my presentation with 2 videos, just to see how the environment of the robot application today. Okay, Ari, can you hear me?
Yes, Prof. Clearly.
Okay, next.
Okay, the operator is Mr. Sadra, Prof. So Mr. Sadra will help you to run the presentation.
Okay, when I say next, just click for my next slide. These are an idea where the IR 4.0 started. We first started with Industrial Revolution when the English first invented the steam engine. That goes back in the late 18th century. Then come when they invented the electricity. That is early 20th century. You know, when Thomas Edison invented electricity. Then come the third part of Industrial Revolution is the automation, where the machine being automated or in the now come in today and the near future, what we call it the Industrial Revolution, which is actually a cyber physical system where it is a combination of the internet with the new ability to direct control the physical world. Meaning to say with the capability of the internet now, with the 5Gs undergoing the 4Gs, and the capacity of computer now, it can control direct, including the machines, factories, that infrastructure that define the modern landscape today, which is what we define the journey to the 4th industrial revolution. So these are the journey that we take from the steam engine. They created electricity, the automation in the factory. Then come now what they call it the 4th industrial revolution, with the capacity of the internet to control our environment now. Next. So actually all started, these are the working definition. If you can see there, these are working with definition that the use of interconnected digital and associated technology in industrial production that enables transformation in terms of people, process, technology to enhance efficiency, productivity, and revenue. The key word here is digital. So anything now that you use is digital. So the student from the IT faculty, they mean to say that digital is the thing now, plus associated technologies, is IoTs with our AI, things like that in the industrial production that we transform the people, the understanding of the people, the process itself, and the technology. Why? Because to enhance the efficiency, productivity, and the income of the nation, to increase the economy of the nation. So this is the working definition of the Industry 4.0, which is they integrated the processes, they use the digital approach that transform the process of the technology now just to increase the productivity and the revenue. These are the working definition of IR 4.0. You can see that they call it, some call smart and connected manufacturing, some call it digitization and integration, some call it, it's a process of disruptive digital technologies. These are all what we call it, some definition of IR 4.0, right? Next. So you can see fourth industrial revolution, how they transform into industry. Actually, it's come from the secondary industries. The primary industries, like, for example, the production oil palm, rubber, tin, so on and so forth. These are all the primary industries. But we are now in the secondary industries. The secondary industry meaning that we transform, we do the process, how to change the primary industry to become a product. So it started with the German government starting initiative to transform these secondary industries into a modernized cybernetic-based manufacturing and production system that are efficient and most cost-effective. Meaning to say that they transform the secondary process, which I will show you later, how this a new environment, IR 4.0, they can use a cybernetic-based manufacturing. They use a cyber security, cyber digital, so on and so forth, right? Then to establish German as a lead market and provide an advanced manufacturing solution. See, these are all started from Germany, as we know that these are the two countries that apply the IR 4.0 very widely. They are Japan and Germany. So it started with the Germany with all the capabilities, with all the technologies. So they coin the words they call it sometimes smart manufacturing or industry Internet of Things. There is sometimes other names given to Industry 4.0. Sometimes they call it smart manufacturing, sometimes they call it Industry Internet of IoT. These are the Industry 4.0. The fourth industrial revolution, they transform it into secondary production, then we call it Industry 4.0. So this is actually Industry 4.0. They do more on the cybernetic, in the cyber environment, and then they use all the production system to be more effective and to be more economically more cost effective. And sometimes they call it IR Industry 4.0 is smart manufacturing. So you must not confuse fourth industrial revolution and Industry 4.0. Fourth industrial revolution is the revolution that transforms the secondary processes into more cybernetic, into more production system, into more cost effective. That is Industry 4.0. Next. So what is this Industry 4.0? Actually, these are the things, as I mentioned earlier, all the cybernetics, all the digitals, all the technology, they are supporting the Industry 4.0. I think these are the things that you people in the information IT faculty have learned about all these things. Things like big data analytics. Now people are, people need, in terms of pandemic now, they are talking about big data now. How to manage, like for example, in Malaysia, we have our own mines justice system, how they can play with the data, how they can control the information, things like that. The second one is talking about cybersecurity. Everybody know what cybersecurity is all about now. How they protect the banking system, how they protect the health system, how they protect the government, how they're trying to protect the military, for example. These are cybersecurity. The next one is the augmented reality. It's not to be physical now, but with the with the IR, the augmented reality, we can make it happen now. Then, of course, the next one is additive manufacturing. If some of you might have get a course in manufacturing, or some introduction into what is manufacturing all about, that you might know what is additive manufacturing. It's a secondary process that we doesn't need a secondary process actually. You just use an additive material to build up a product. Meaning to say that you want to make this mouse, for example, right? You doesn't need to have a primary process. So with the additive, with the layering of the process, you can produce this mouse easily, very fast, efficient, and cost-effective. That is what we call additive manufacturing. Then the next one is system integration. And this we will see widely how the automation come in, how we integrate the production system, the office automation, how we integrate all the processes into one system. Then the next item is simulation. I think we know the word simulation. In manufacturing, actually, we do the simulation first before we can do the actual production. We see how the process is being made. Is it possible? Then we do the actual processes. Then now this is what we're talking about, the autonomous robots. These are things that we will discuss today because robots is only an enabler. It's an enabler to help the process of art, what we see Industry 4.0. This is the topic today that I will deliberate more what we mean by autonomous robots, or more specifically on industrial robotics. Then the next one is cloud computing. I think you know what is cloud computing all about. We don't store our information, our data on the hard disk whatsoever. It's now that we can do it in cloud computing. Last but not least, the IoT. That the thing that now in any application that we can use, we use IoT now, right? So these are 7 or 8, 9 items that supporting the Industry 4.0 systems. So without this 4, that it cannot be as a complete Industry 4.0 actually. So these are the things that contributes, or these are the things that the what we call it that support the Industry 4.0. So for example, if you study like cybersecurity, is part of Industry 4.0. If you study augmented reality, additive manufacturing, these are that make the ecosystem, yes, the ecosystem of Industry 4.0. But as for today, we try to look how robotics, how industrial robotics contribute in the Industry 4.0 in a special, in more specific way, how the robotics will contribute in the Industry 4.0. So remember, these are the elements. These are the things that contribute to the Industry 4.0: big data, cybersecurity, augmented reality, additive manufacturing, system integration, simulation, robots, cloud computing, and IoT. These are the elements that contribute Industry 4.0. If there any question while I'm giving the lecture, you can interject me, Pak Ari. Sekiranya ada apa-apa persoalan boleh tanya saya kalau ada mau diterangkan. So these are the element of Industry 4.0.
Maaf Prof, diskusinya interaktif atau nanti ada sesi tersendiri? The discussion will be interactive or we can hold it in another session maybe?
Okay, we can have question and answer after the presentation.
Okay,
right.
after presentation. Okay.
Fine.
Thank you very much, Prof.
Okay, that's good. Okay, next. These are the challenges. We're talking about Industry 4.0. We're talking about the advancement in processes. We're talking about cybernetic. We're talking about big data. We're talking about additive manufacturing. We talk about cloud computing. But these are the challenges that we have to know before we go into Industry 4.0. It's not that straightforward for us. We can implement Industry 4.0. One of things is the awareness. So it's not only the student, even the public must know what is this Industry 4.0. If we can understand it, but the public or even among the student or even the docent or lecturer, if you don't really grasp the Industry 4.0, it's even difficult for us to implement the system in our system. Okay, then it's a very high scale investment. That's why when the Germany started this Industry 4.0, they have all the economy, they have all the financial capabilities, because it's not that cheap. It's not that cheap. Remember, it's not that cheap for us to have the integration, to simply replace a human by a robot, or to simply replace a production system with a manual into a more fully automatic. And it's not that cheap for us to bring in all the computer capabilities into the system. So bear in mind that it's very costly, it's very expensive. And we need a very commitment from the top and from the management or from the government to really support in terms of monetary to do our Industry 4.0. And then it's a collaboration culture. In Industry 4.0, you cannot work alone. For example, if you are from an industry, for example, in manufacturing industries, you need to collaborate with other systems to come in. What are they? For example, the supply chain system, how the supply chain system can come in, the production system. These are, you need to collaborate in order to ensure that the Industry 4.0 is successful. And again, data and cybersecurity is concerned, because you have to share data. You cannot keep data on yourself. For example, right, in the banking system, for example, you need to share data. In production system, you need to share data of the machine component. You need to share data with the company. So there must be some, as I said, the security, the data security, cyber security must be there. As you know, in the society now, there are hackers everywhere now. I mean, now even especially in the banking, nowadays you can there are people who are trying to hack the system and to make a mockery of the system just to go into the data. So there must be a good cyber security system in any application that do. That is very vital. For example, like in the government, for example, if they want to use fully automated or fully cybernetics, they must ensure that they have a very secure cyber security. Then digital readiness, as I mentioned earlier, the Industry 4.0 is all about digital. So you have to willing to change the system, the mentality from a normal to a more digital now, right? So make sure that people understand the readiness to change the digital itself. Then the next one is the skill, the know-how. This is where our student in Malaysia or even in Indonesia, that we have to give the skill, the know-how. Not everybody now is capable to operate. Not everybody now, especially in the factory. We have to train. We have to train our workers. We have to train our programmers how they can be environmental friendly with the system, how to operate, for example, the computers, the AI, for example, the programming, for example. Say they must be skilled, not only industry 4.0, but in any aspect of life, you must have skill, right? So the skill is important for us. The last but not least is the best practice. We need to see how people are doing that. We have to see what are examples, what are the success story that we can implement Industry 4.0. Because people like us in Malaysia or in Indonesia, we still at the level of, not fully grasp of this Industry 4.0. We may talk about it, but if you compare us, for example, with, as I said, in Germany or in Japan, or some part of the Europe, they are much more advanced. Why? Because, as I said, the challenges, they are much less. They have the money, they have the people, they have the technology, right? So, but now we are, in the Nusantara now, we need to have that level so that we can apply. Yes, we can apply now. I believe that in Indonesia, even in Malaysia, certain aspect in the government, in medical industry, in military, whatnot, we have done it, but not to the fullest of the technology. So these are the things we as a lecturer, we as entrepreneur, we as engineer, and you all as what you call as students, right? These are the challenges we must have to be in mind for us to be successful in Industry 4.0. Most importantly, the government, see, because most of us are more government policy to implement. If the top is understand what is Industry 4.0, then we might get good support. So these are the challenges that we have to bear in mind. What is Industry 4.0? Very high scale investment, very expensive security. We need to work together. We have to ready with the digital world now, the skill and the best practice, right? Next. These are the some benefits. Why we need to go to Industry 4.0. We must go into Industry 4.0 because we can see the flexibility. Why we are now go for Industry 4.0? Because the flexibility, higher flexibility given by small batches production with the economies of scale of mass production. For example, when I'm talking about the what do you call it, the manufacturing just now, the additive manufacturing, you doesn't need many machines. You just make one or two big machines to produce a part. Then you have a very small environment that you don't have a big factory now to produce a part. Secondly, in the 20th century manufacturing, that we manufacturer, we don't produce 100% of ourselves, right? Because we need that flexibility. We can get some other parts from other countries, so they give more highest flexibilities for the small batch production of economies. Then the speed, we need the speed in any what we call it, in any world or any manufacturing or in marketing, you must have the speed. If you late into the market, somebody else come to you. From prototyping to mass production, right? Once we design the product, right, they must be into the market very fast. So you cannot delay the time. So once you get the product right, you have to produce it and into the market, or else you lose the competitive in the industries. So the speed is there. Industry 4.0 help us with the speed to go into the market with the new technologies. Then optimization. So it optimizes productivity, efficiency to the lower setup time and reduce downtime. So when the robots are there, when integration are there, the production time increase and the downtime decrease. This is where we will see how we replace some of human activities with robots and other things that to help us. So the optimization is there. And of course, about the quality. You can see now with the use of smart manufacturing, as we said earlier, or Industry 4.0, we improve on quality and scrap reductions. because of the real-time production through the advanced sensor. Because with the controlling, as I said earlier, with the controlling of the using the internet, whatnot, we can control, we can monitor using sensor, because sensor is another technology. I think we talk about sensor later, because now in Industry 4.0, sensor is another important thing that we have to understand, because it's all about controlling. So sensor, the heat sensor, the wet sensor, whatever sensor that will help us to determine the quality of the product. Last is the competitive. So now we are in the world of very competitive world now. We got to compete with each other. We have to stay in the market. So we need to apply Industry 4.0 for us to survive. For us to survive in the real market now. Because as I said, high competitiveness of products and business with the level playing field through cooperation and confederation of the firm. So we have to be competitive in the market, because with the product, we need this cooperation. Remember that the cooperation of the sector. So these are the benefits that give. Even as we will see that in the use of robotics, these are, we can see that the flexibility, speed, optimization, quality, and competitiveness. If you take one of the item of the Industry 4.0, for example, the robot, these are the benefit that robots can bring to the system, right? Next. I will go briefly. I mean, I think probably most of you have know what is robot. You know, these are some definition that I'm coming to the part 2 now. First part, just now we're talking about some idea on Industry 4.0. Now I go straight on the industrial robotics. What is robot? Because it all started with industrial robots. We're talking about all this safety, we're talking about, as the Dean was saying, that you can see all these different robots, humanoid, so on. But it's all started with the keyword of robots. So these are the definition that we may come across what is robots. It comes from the word from the Czech. Robota is a worker of force level. From the Czech player, he call it somebody is in 1921. They created the word robot from Czech Republic. But in general, it's a general purpose reprogrammable machine processing certain anthropomorphic characteristic. It's a general purpose. That's why I said the robot is an enabler. It's a general purpose. You can ask the robot to do anything, from pick and place, from helping you, from the industry, from any system. It's a very general purpose, and it's programmable. And this item is a programmable. Robot is programmable. It can be programmed according to the application that you need. What type of the program that you use, we will discuss later, but it can be programmed. So another characteristic of robot is can be programmed to process certain, so programmed to process certain anthropomorphic, meaning to say that it can process into mimic the action of any people or any being. Like for example, as a human being, to lift the feelings, to do some work, right? So it can imitate. It's a general purpose. It can be programmable. It can be programmed and can do and can imitate any action that we ask them to do. That is as a general definition of a robot itself as a general. But in industrial automation, in industrial robotics, we call it like ISO international standard. They call it automatically controlled. It's a controls automatically, programmable, and multi-purpose manipulator program in 3 or more axes. Because one of the component of a robot is the manipulator. Manipulator, the one that can use, as I said, to pick, to place, to feel, and they can be in a 3 or more axes. If you are in manufacturing, you know what I mean by 3 or more axes. That means you have X, Y, and Z. Or X, Y, and Z, you can have a rotation X, rotation Y, rotation Z, rotation Z. So we have more axes so that the robot can move freely in the more axis. But for Robotics Institute of America, they call it reprogrammable. That means you can program and reprogram again and again. And it's multi-function manipulator. The manipulator is multi-function. They can use a different function of the manipulator, right? For example, to move materials, parts, tools, or special device to variable programmable motion for performance of a variety task. We will see some of this action later in the video, how this robot being used in industry or in other situations. The last one by the Japanese, a device with degree of freedom that be controlled. So basically, from all these things, we can take an understanding that robot is just an enabler, a general purpose thing. It can be programmed and reprogrammed. It can do anything that we ask them to do as what human can do. And then again, he have the degree of flexibility. In engineering, we call it either 2 or 3 axes, and can do anything that we instruct them to do. So even though we can see a robot can do many things, but it's all from the brain of the human, not the robot. The robot is not that smart. We are the one who program them, right? If you look all these cyber film, whatever this thing, these are all men programmer. It's not the robots, right? So these are understanding for us best to understand what this robot all about. Okay, next. Yeah, why we use robot? You know, Indonesia have what? How many million people? 200 over million. In Malaysia, we have about 35 million people, right? So why we need to use a robot? We have people now, and it's more cheap robot. But again, we need to use robot in environment where it's very hazardous, where the environment is not safe, for example, where environment is very dangerous, for example, right? Then we use robots to help in that kind of environment. And we need a repetitive work cycle. Sometimes human a bit boring. You ask them to do a few things repetitively, they get bored. When they get bored, right, the quality is not there. The perfection is not there. But robot doesn't matter. You ask them to do 1,000 times, they do the same thing, the same part they will produce. So any repetitive work cycle, robot can help it. Sometimes this is where human cannot compete with the robots. We feel tired, you know, we need a break, we have to go for lunch, things like
Hello, Prof. I think we lost the signal again. Hello?
okay. Some interruption just now. Can you hear me now?
Yeah, we can hear you clearly, Prof. Okay.
Ari, can you hear me now?
Yeah, we can hear you clearly, Prof. Okay. The signal is stable now.
Hello?
Yeah, hello?
Hello.
Can you hear me now?
Yes, can hear you clearly,
All right,
Prof.
then.
Okay,
Let me continue again.
yes.
These are all technical issue, right? Okay.
Yeah.
So, as I said again, why we use robot is a more repetitive work environment. And then they have multi-shift operation. You can ask them to work 24 hours. You can ask them to be around the clock to work. Like human, the most maximum we can work 8 hours, but for the robot they can work round the clock. They can do multi-shift operation. Then they can do infrequent changeover. That means to say that if you want to change from operation to another operation, they can do anytime. Another operation, they need some training to do that, but not robots. As I said, you just reprogram them. They can do the changeover from one process to another process very fast. Okay. Then part position and orientation are established in the work cells. Then you say that one we program certain part to reproduce, right? Then can be established in a small work cell that can work together. For example, you have different kind of robot to work together to produce a component, for example. So any part position, they can do that in the work cell. Then, of course, the last one is difficult handling tasks for humans. And these are normally, you can see that some robot being applied in military, for example, some being applied in security, for example, some being applied in the very difficult handling situation. And this is where we know now, like the humanoid robots, they can apply in this situation. But the concept is still the same. The concept is still the same. Another thing is that consistency and accuracy not attainable by human being. This is again, the quality come in. When can you produce the part very consistent and very accurate, the quality which goes up, right? When you apply the robots, for example, they are not being tired. They don't have fatigue, for example. So they will produce the part very high quality. That's why one of the advantages of the Industry 4.0 is the quality. Why? This is the way they produce the part where human cannot achieve it. So for any consistency and accuracy, they use robots, right? So this is where you can see in the industrial manufacturing, especially in automotive, for example, where the environment is not very conducive, the environment where people cannot work 24 hours. So that's why they apply the robots. The next one is reprogrammable. As I said earlier, you can program anything that you ask them to do from one process to another process, and you can change them anything that you like. It's very flexible. The last one, most robots are controlled by computers and therefore to be interfaced by other computer systems. One example is CIM, is integrated manufacturing, because as I said, robot cannot work alone in the system. Remember that in the environment of Industry 4.0, the enabler, there must be a system integration, right? So they must be interfaced with other computers. There must be interconnection with another element in the factory, so that it can be controlled. It must be controlled by computers. That's why when we talk about cybernetics, we talk about IR, we talk about 5G, things like that. So it has to be controlled by computers. That's why when the capacity, when the what we call it, the power of a computer, is going up to a certain level, and where this is made possible for us to use 4.0. So some reason thinking why we need to use robot where we have many people, but sometimes too many people, you cannot have in terms of economic terms, it's much safer and much cheaper in certain operation to use robots. Okay, next. These are some history, how we first started. As I said, it's not new. I just browsed. This is not new robots. It has been there long ago in 1937, and it's go back to 1956 again when the first industrial robot was used. Unimate, produced by Unimation, founded by Joe. As I said, robot is nothing new. But why is now we're talking about robots in Industry 4.0? Right? It's there in early 90s. You see, Even in Japan, in Germany, you can see 90% of the factoring environment is controlled by robots and controlled by machines. But the thing that makes it possible now, because of Industry 4.0, because the capacity, the strength of the computer, the digital, the database, things that mean robot is more widely used. It has been there. It's nothing new about robots. It has been there, but now it's more, as I said, it's more needs now to use robot because of the environment, of the capability of our computer power now. That's why they used to be a work alone robots, right? But now when we have integrated, they come to become a system. They can produce production is more fastest, productivity highest, and the quality. So you can see now that industrial robot is not new. It's been there from 1937 up to 1956. Even some of the robots are still in use now in terms of concept, right? These are where we started the industrial robots. Next. Okay, in 1966, they started with all the 6-axis articulated robot designed to permit arm solution. 73 KODE robots in bringing robot to market. These are all the development of robots in the history. From 37, 65, 69 to 1933. These are all different advancement in the robot itself, from 2-axis, 6-axis, and then they know a certain to do some articulated. For example, you can see here that how okay, these are, you can see how on the right hand side they have big improvement now. From a for one single robot, they program it, they do some research, they improve it and improve it. So the robots now can do some multi-function now. You see a different axis, a different movement, a different type of technology has been applied to the robots. Right? Next. So in 1984, they applied SCARA robot. SCARA robot is a systematic robot, which I explained. This is a different kind of robot to different function. So they have a different type of robots with a different function. One of them SCARA, which I will cover later in the lecture. So they have SCARA robot. The 92 in Switzerland, they call it the Delta robot packaging application. They use robot for the packaging. Then in 1998, ABB is an industry in Sweden. They develop a flex picker, they call it, the world fastest packing robot based on Delta robots. And they can allow to pick up 120 objects in a minute. So this is how they have applied. You can see the repetitive work. They can show that how fast the robot can do the job. Next. Then not very far again, in 1999, where they developed better place the need of external beam guiding device and to allow use laser in combination with the robot with high. So they even use in 1999 they use what we call it a beam guide device to help the robot now. Now you can see in early 2000 the Japanese come in. Now how the Japanese come in early 2000, where 2004 you can see from the history, robot is first started in the West from Czech Republic, from Sweden, from Switzerland, but it first started in the Western bloc. But only early 2000 the Japanese come in to use the concept of robot. But now, if you look into the market now, the most robots you can find in the industry is in Japan. That's why now, if you look like, as what mentioned by the Dean earlier just now, all this kind of robot is first developed in Japan now. If you go to Japan now, you can see their system is almost 60 to 70% of the operation is controlled by robots. So when the Japanese come into the industries, they have overtake the robot industry from the West. So that's why now in early 2000, the robot, they call it Motoman, right? They used to improve the robot control system, which provide the synchronized control of 4 robots up to 30 axis. That means this is where the Japanese come in. They integrate it. They can use 4 robots. Normally, we thought the robot can use 3 to 6 axis. With the integration, the Japanese can integrate the 4 robots to do up to 38 axis operation. So see how flexible they can do the manufacturing. I've seen early 2000, about 2004, 2005 in Toyota, for example. And Toyota, as you know, that is the biggest automotive industry in the world, is Toyota. And how they implement almost 80% of their assembly and operation using robots. So they are catching up very fast in industry in Japan. Next. Okay, that's about some history. It started in the Europe in 1937. Then they developed from 1 single axis to double axis, 3 axis to 6 axis. Then improved from other function, from pick and place to packaging. And then the industry is getting better now when the Japanese come into the industries. Right, so these are the history that how the robots come into today, how the application, how they improve things like that. So basically now I can go very roughly on what are the anatomy. Anatomy is the part, like the human anatomy, what is all this robot about, right? Let me start. For us to understand, for any kind of robot, they must have certain anatomy. Whatever kind of robot, either the industrial robot, either the humanoid robot, whatever, they must have this characteristic, this anatomy, for them to function very well. Okay. First, there are joint provide relative motion. They must have joint. You can see there are so many joint. Joint 1, joint 2, joint 3. Like us in human being, if you look at your arm, you have so many joints. Your elbow, your wrist, your shoulders. This exactly, as I said, they are mimic, they are copying what we can do. So that they must have the same, almost same anatomy like a human. So they must have joints, because this joint that provide them to move. They cannot have a joint, like for example, the gripper. Like us, we have a wrist, right? To move our wrist. So they have a gripper there. So we have our hand, our wrist, our elbow, our shoulder. Same with them, they have joint 1, joint 2, joint 3. So this will allow them to have more flexibility. So then from the joint, they are linked. Like for example, our fingers and our hand. Not the joint, then we link. So they must have a link. And the link must be very rigid. If the link is not strong, for example, if our wrist, our hand is not strong to pick up things, we will drop. That's why the manipulator in robots, for example, they must be very strong. Not too strong and not too hard. They can feel. So for example, if ask the robot to take something so that it don't grip too hard, it will break the things. If it's too soft, the things will drop. So these are we played by the sensor again, I said. So they need a sensor to have the feel of the force that they grip, right? So they have joint, they have linked, and they have various types of movement. Look at our arm, we can rotate, we can go straight, see? So that's why robot, they have different types of movement, either linear, straight line, or they can rotate. That's why in industry, you can see at this figure, you can see at the end of the arm, they can rotate. The link, they can move from A to B, B to C. All right? And the next one, what you call it, degree of freedom. So they must have certain degree of freedom. Like our hand, we have indefinite degree of freedom, but robot has certain what you call it, certain degree of freedom they can do. So the robot has certain degree of freedom. Like for example, if their hand, so to what degree they can rotate. If they arm, to what degree they can move. So this is to show that the flexibility, how they can do work. So we call it the degree of freedom. Okay. For example, if a robot have two joints, for example, the wrist and the elbow, they have only two joints. All right. They have only 2 degrees of freedom. That means to say they have rotate, they have move only. They cannot go up, they cannot go down. So this is what you call degree of freedom. How many movement they can do in one task. So what you call a degree of freedom. So that's why, therefore, a robot with n joint and has n degree of freedom depend on n joint. If you have 3 joint, probably they have 3 degree of freedom. But probably with the wrist, you can have another degree of freedom. So that's what we term it in robots is the degree of freedom. What extent they can move the manipulator. Normally a robot possesses 5 or 6 degrees of freedom. As I said, they have a minimum of 5 of, as I said, they can move X, Y, and Z. They can rotate within X, Y, and Z, right? So they have at least 5 to 6 degrees of freedom. Then the last one, they must have gripper. Gripper, what I said, gripper is our finger. They call a gripper. And this gripper, they must attach to the end of the arm. You can see that in the figure. The gripper might be attached at the end of arm. You can see at the robot there, it's called end of arm. So like it's our hand, like our palm, our finger is attached to our end, is our wrist. So this is the one is important in the robots. Because this is the one to do most of the function. Apart from the degree of freedom, apart from the joints, the gripper that determine their functions. Because certain gripper can hold certain loads, certain kilogram. Certain gripper, they need to feel something. Certain gripper, they have to feel the heat. Certain gripper, so the gripper play an important part in the robot anatomy, actually. Right? For example, like in home robot, for example, okay, and medical appliances, for example. So this gripper is play an important part, how to do the function. So these are the anatomy of the robot. They must have joint. They have to be linked. They have a degree of freedom, right? And there must be minimum 5 to 6 of freedom. And most importantly, they have a gripper to handle a workpiece and must that attach to the end of arm. These are in any robots, whether I said in industries, in home application, in whatever, they must have this anatomy for the robots. Right, next. Some as I said earlier, you see, the robot manipulator consists of 2 sections: the body, arm, position, object in the robot's volume. The wrist, they still use the word wrist assembly for rotation robot, and function of the body and the arm assembly to position and effector. Sometimes the end effector, they call it gripper, as I said earlier. So these are the manipulated joints. You can see that. These are, you can see it on the top figure there, the linear joint type L. This is we call linear joint. Then you click on the right top hand side, you can orthogonal joint is O, is more an orthogonal. You can see the joint motion to the left, to the right, and up and down. Then you can see the rotary motion. As I said earlier, it can move in any axis, or they can twist. Move is one thing, but twist another thing. Then the last, they can revolve, they can rotate. So normally, they use this assemble, linear, O is orthogonal, R is the rotational, T is the twist, and V is the revolving. So these are the terms that you use in robot, how their movement being termed. So that when you do the program, right, later on, you must know which movement that you need to program. Is it to program the wrists, the field, you have to move it, or going to rotate it? So these are the flexibility that you have to understand in the programming. These are the example. For example, I give the example down there that TLR. That means the robot can do turning, linear, and rotational, and they can also have translational and rotational motion. So separate body and arm assembly using a certain column. That means certain. Let me say that in certain operation you have to identify this robot to do what certain function. This have to do what function. These are normally the term L, O, R, T, and V that you use in robots. Okay. Next. Okay. From the anatomy, we know the term NR, just now, but this movement we translate into a different types of robot. For example, we have 4 type of robot. The Cartesian. The Cartesian is more like axis. Then we have cylindrical robot. It can move cylindrically, it can roll. Then we have polar or spherical, and we have joint arm or articulated. We have SCARA. From can I have the slide before this? The slide before this. Can I have the slide before this? Yeah, these are LORTV. For this monopolar giant, they have a certain robot. Not all robot can do all the 5 operation. See, not all robot can do LORTV together. No, that's why we have this different kind of robot can do these 5 different function. Okay, remember that certain type of robot they cannot do all. For example, I said they can only TLR or TR only. They cannot do LORTV all together. They cannot do that because there are some restriction in designing a robot. Not every robot can have the function of all the 5 what they call it, the motion, right? The manipulator cannot have all these 5 functions. So that's why. Next slide, please. That's why you have Cartesian, cylindrical, polar, joint, and SCARA, right? So these are different types of robot have that configuration, the 5 configuration as mentioned to you earlier. Okay. Now let we see what are these industrial robot configuration all about. Next. Like for example, this is a Cartesian configuration. They can have only longitudinal and orthogonal only. They can have 5. Remember, they can have longitudinal and orthogonal. So they have, for example, you can see they have L longitudinal up and down. They can have O orthogonal left and right, up and left and right, X, Y, Y, and Z. So as X, Y, and Z. It's like axis. It's Cartesian. So this type of robot with only LOO movement, or we call it X, Y, and Z robots, because they can move into very straight X, Y, and Z direction only. Because this will apply to a certain function in industry. For example, this one they can take and place X, Y, and Z. They can move, take and place, or they can put some products on the machine, for example. And this is what we call Cartesian robot. Next. So these are the advantage. They can do straight line insertion into furnace. For example, you want to put some product into the furnace, very hot. You can use this type of robot, and easy to program. And they have rigid structure for certain products. What are these advantage? Because a large operating volume, because it's quite big, right? They are exposed guiding surface require covering and corrosive or dusty environment because the robot is exposed to an environment and oxidation, rusting, things like that, because the environment that they're working good, and can only reach front of itself. They can only reach in from the front, cannot go for the back. And axis are hard to seal. The axis, you know, the joint is difficult for us to cover, things like that, right? That is Cartesian robot, or we call X, Y, and Z robots. Next. These are some example. For example, they use here more on assembly, welding, and to glue and material handling. For XY robot, they can use this other operation for assembly, to do some arc welding, to glue, adhesive, or to handle material handling. And you can see the payload is 5 to 100 kilograms. The payload means to say that the gripper meaning to say that the gripper can hold to the components, minimum is 5, maximum is 100 kilograms. That means when you design a robot using this Cartesian, that you have to know what is the weight of the component, right? And they are very fast. They can move X, Y, Z very fast, very quick, very competitive. And as I said, they have only 3 axes or 3 degrees of freedom. These are Cartesian robots. Next. These are gantry robots, and they have a big gantry at the top. Gantry, they can move from one place to another place. Like for example, the packaging just now I mentioned earlier. So they can handle very large parts. They can move material on long distance, and they can even use the welding and gluing also. This is quite big. They can repeat the thing between 0.1 to 1 millimeter. Still, they have 3 axes, but they need a very working big what called a working envelope, big working area. And this one have a big payload. They can go up from 10 to 1,000 kilograms. Because it's so big, that means the speed is quite slow. So they are still Cartesian, but we call it gantry robot. Okay, they to handle big product. Next. And now come cylindrical. Just now is a Cartesian. Now, because Cartesian just now they can use COO on O, but this one they can use translational motion, longitude, and orthogonal. Now, from get configuration, you can see that look at the axis, the 3 translation they can move longitudinal, up and down, and the orthogonal. Okay, they have a vertical column. They have assembly to move up and down, and the arm can be moved in or out to the column. That means the arm can move up, out, and out to the column. And this is what we call a cylindrical robot, because they have cylindrical movement, which is T, L, and O. Okay, next. This advantage can reach all around us because it can rotate. Most of the environment they can reach. As I said, rotational, it rotates itself, and easy to program like Cartesian, and they are very rigid to handle heavy loads. You know, it can 5 kilo to 10,000 kilogram loads, payloads, and a good access into cavities and machine opening. That means they can rotate, they can move into certain areas to load the machines. This is a cylindrical robot. But again, they cannot. The disadvantage, you cannot reach above. The linear is quite hard, but won't reach around some obstacle. If there any obstacle, they cannot handle it. Then again, exposed drivers are difficult to cover from dust. So the driver itself, I mean, the joint is difficult to cover. Next, quickly, which time now? These are some application of the cylindrical robots, as I said just now. There are small robot, precision for small assembly tasks, robot handling machine. That's why you can see some industry like SME, small and medium industries, when they want to do some pick and place, when they do some packaging, they do apply this kind of robot in very small scale. In very small scale, as I said, not a fully integrated, because they have certain function to do in that industries, for example, right? So they have a bit different sizes, they're very fast. Still, they have limited access, or we call it the degree of freedom. And the working envelope, the working area, is just a vertical and radial stroke. And the structure is not that hard, it's not that sturdy, it's not that compact. And they can handle a very less small load, maximum 200 to 50 kilogram. If compared to the cylindrical just now, they can go up to 10,000 kilogram. And again, as I said, it's inexpensive for their size and payload. That's why I said it's a certain industry, in a small and medium industry, we need this function. They can afford to buy this kind of robot into their factories, into their processes. Next. This is the next one, call it polar or spherical. Yeah? Just now it's rotational, but this is spherical. It's like a spear. Okay, they can move into three transitional, rotational, and latitude. So you can see at the configuration there, they have the L joint, the joint, the L1 joint, and they have transitional joint, and they have rotational joint. They have three now, T, R, and L joint configuration. That's what we call. You can see that they can move the L longitude, they can rotate, they can do transitional movement. But this is another one, we call it polar. Just not cylindrical, but now we call it polar configuration or spherical configuration. Next. Advantage, they have large working envelope. That means they have the robot can reach in a very wide, in a more area, what area can reach, and they have 2 rotary drive, right? And it can this drive can be protected from dust and liquid. That means it's good for an environment that's very unhealthy environment. But the disadvantage, the complex coordinates more difficult to visualize, control, and program. And again, the accuracy is not as the not accuracy as the Cartesian and the other robots. So they have low accuracy in spherical robots. Next. These are the example. You can see the structure there. These are the different application for spherical robots. You can see they have only three to the payload also not that big, only 100 kilogram, and the speed is quite low compared to the previous robots, right? And the application is more metal handling and spot welding. For example, like in automotive industries, they can use this kind of robot for welding, to do the spot welding for the car. Or they can use for machine loading, meaning to say they can load certain part into the machine. So they use this kind of robots. Next. These are the more versatile, let's say, call it. So these are the first figure that I show in the slide. This is the articulated configuration. They have TRR, they have transitional, they can do rotational at all the axes, X and Y axis, they can rotate. And general configuration of human, they are more like a general human arm. They can, this kind of joint arm or articulated configuration, they are more like human arm. They can imitate like human arm. So what a human arm can do, this robot can do. And they have all axes move in angular direction. For example, they can pick the place, they can rotate the component, they can put the quantum back into the machine, they can come back. It's exactly like what our arm can do. They have all the links, they have the rotational, they have transition, they can rotate This is exactly, this is most of industry now are using this kind of robot. We will see that one in our video. Okay, this is the last one, articulated configuration. They have T, translational, rotational, and rotational. Go to rotation, X and Y rotate. Okay, next. They are all rotary joints, allow for maximum flexibility. They can rotate the advantage. Any point in total volume can be reached. In any envelope they can reach. They can reach for the component, and all joint can be sealed for the environment. That means the joint, like us, this, you can see that our wrist, our elbow is all can be joined. That means it's not exposed to the environment. It's completely safe. Less maintenance for that. Again, disadvantages, difficult to visualize because they can move more all the time, and difficult to program. It's not difficult, it's quite complicated, right? Have some volume restriction. Again, the accuracy might be low as compared to the other. Even that it can move freely, but the accuracy is still low for that one. Okay. Okay, these are the 5 types of robots that normally used in industry. Next. These are the example how they use articulated arm robots in welding, painting, sealing, deburring, and metal handling. Like for example, to do the painting of the car, for example, they use this kind of robots because the accuracy is not important, because what they do, they just do the spray. And then material handling, deburring, meaning to say that if you have any product to be deburred, right, the product can be use this project, and welding also. So these are most applied robots especially in automotive industry. Next. Oh, there's another one, SCARA one. Sorry, SCARA stands for Selectivity Compliant Assembly Robot. They have V, R, and O notation. You can see that they can rotate. They can have V, vertical there, vertical movement there, and similar joint arm like articulated, except that the rotational vertical axis are used for shoulder and elbow joints. You can see that they got only the arms, but they have the one there is an elbow joint. That what is called another configuration. It's called SCARA, Selectivity Compliant Assembly Robot. But this is only used for assembly robot, right? This is the last one. Yeah. Next, we call it SCARA, VRO. They have high speed, high axis rigid, large working for space, moderately easy to program, and the disadvantage is a limited application, only in certain application, and they get two-way to the point and difficult to program offline, and high complex arm they have. Okay, these are the SCARA robot. Next, these are the example. These are example like screw SCARA robots. You can see at the picture that is called it Fanuc. Fanuc is a Japanese man because there are many industrial robot manufacturer in the world now, like KUKA is in Europe, Fanuc in Japan, even Mitsubishi. You can see different type of manufacturer of the robots, because certain industry, for example, like in Toyota or in Mitsubishi or in Germany, they design their own robot. They design the robot to do a specific task. They cannot buy the robot off the market. Can you understand me? So certain big industry, they design their own robot, because as I said, robot is a design, you can program. So they probably not to use these 5 type of robots, they have their own design. Like Fanuc, for example, Fanuc is a machine, is a company that do the controller, but they also do the robots, for example. See? So these are the industry now. If I'm using my industry, I need certain robot is can find in the market, or these 5 types of robots. I design my own robots to certain function. So that's why you can see a different brand, Fanuc, KUKA, Mitsubishi, you name it, it's all in the market now. Next. Just now we're talking about the axis. Now we see the wrist. This play an important risk, right? The risk have three functions. Is the what you call is the roll, the rotate, is the jaw, is rotate, is the jaw, and is a pitch. So these are the three risk configuration. In any robot, as I said earlier, they must have this risk configuration that they attach an arm, because the flexibility of the robot, of any kind of robot, depends on the risk configuration. Apart from the axis movement, which we see earlier, but another important thing is the way you attach your gripper. So the risk is where you attach your gripper just now. Like is our you can see that this is our hand. We attach, this is our wrist. We attach our hand and the wrist. So these are the one that important. We can roll, we can yaw, we can pitch, we can move. So these are the 3 degrees of freedom they have now. For the wrist, they can roll, they have pitch, how deep is that? And they can yaw, they can rotate on the other axis. So any robot that I mentioned earlier, that the wrist configuration is important, because they said that wrist assembly is attached to an arm. So any robot, they must have a wrist to attach. That end effector is attached to wrist assembly. End effector, or we call it the gripper. They call it end effector, either the gripper we call it, or hand, whatever. Then the function is to assembly to orient an effector. That the body and the arm determines the global position of the, because the body itself will determine the wrist itself on the function of the robot itself. So they have 3 degrees of freedom: roll, pitch, and yaw, they call it. The notation normally we use in robot, we call RR and T. So apart from the axis, whatever, the wrist configuration is important from the robot. Okay, next we have now, I got reminder, I have another 10 minutes. Okay. Yeah, Pak Ari, give me another 10 or 50 minutes. Let me finish it quickly.
30 minutes.
Yeah.
30, not 10, 30 minutes.
How much time do I have?
30 minutes, bro. So 30 minutes left. 30.
Because such an interesting topic, it's got big to cover. But I do it quickly. Okay.
I'm sorry, bro. Just a reminder.
All right. Another thing is we call it work envelope. Of all these 5 different of the robot, they have certain work area they can do. So the bigger is the robot, is the bigger the working area they can move. For example, is you have a bigger arm, that means the bigger area that it can reach. And this is what we call the work envelope. That means the work volume, work space, or robot to reach. So any term. For example, you have to design the robot, you must know how big, how far the robot can reach. Okay, so if you want to buy a robot for your application, you have to determine the physical configuration. Either you have to buy SCARA, you have to buy Cartesian, whatever. You have to do the Cartesian physical configuration. You must know the size. If it's big, more, and then you know the axis. How many axes? Then you must know. Remember where the robot to be mounted, and the limits. These are the criteria that envelope robot, like a mission. You must know that how far the robot can reach, the working area. So that's what we call the work envelope. They said here work envelope is one of the most important characteristics to be considered when you selected a suitable robot, because the application space should not fall out of the selected robot reach. If you have small work space, you have to choose a small robot to work within that envelope. You know what I mean? Like, for example, you can arrange the robot in very series, but make sure that each robot, they must not collide each other. They have their own limit or specification. So this is what we call normally the work envelope. Next. These are, as I said, For example, like for the Cartesian, you can see the fit line there. This is the area that the envelope can work. You can see like an envelope there. You can see the line there, right? The Cartesian, as I said, they work in a very like rectangular X, Y, and Z. The cylindrical is more like a cylinder. They can work, and the polar is like more of a, what you call it, like a globe. The hollow spherical works envelope. This is to show you this kind of robot, they can work in this kind of area only. Okay, so we have to choose which kind of operation that we know, so that we know this robot can work in this kind of area or work envelope. Okay, next. Next slide, please. Okay. This again another configuration. You can look at the SCARA. You can look from the top view. They give you some what you call it, some configuration, some calculation to a certain area, to a certain length that the robot can work. You can see from this configuration, you can see how big is the robot can move. These are normally we specify the work area so that we know when we design, when we assemble, when we integrate, we know these are the area that the work the robot can work with it. Okay, next. Okay, this is another important thing. After we define the type of robots and the things, that we are now into the end gripper or end effector of an industrial robot, because this one will be applied, as I said earlier, to any kind of robots, whether it's industrial robot, whether it's military robot, whether it's whatever. Okay, this one will determine the design of the what we call end effector of the industrial robot. There are special tooling for a robot that enable it to perform a certain task, like our finger. We call it effector, or either we call it a gripper. It can grip, or we call it a tools, because at the end gripper you can attach either a gripper or you can attach as a tool. For example, if I want to use the robot for pick and place, so use a gripper. They can pick and place. We use gripper. But if one ask them to do some spraying or welding, so we can attach a spray or welding at the end gripper. So both are what we call end effector, either a gripper or a tools. Gripper means to say that they are used to pick a thing. Tools to say that they want to do certain function in manufacturing, either welding or spray. So this will determine the function of the robot. For example, you want to use pick and place, you use a gripper, like the Cartesian is more. But you want to use for spraying, you use a cylindrical robot, for example. You change the tools to be attached at the end gripper. Right. These are what we call the end effector, either gripper or tools. Okay. So the design normally, and for a student, normally for my student, I would like them to design the gripper, because this gripper will determine how we can use the sensor. What is the force that you can grip to what degree? For example, you want to hold a certain bottle, certain weight, so you have to design this gripper. So most of in the labs, normally that more from programming is the design. For me, like in manufacturing, you are more important for us to design, right? Mostly on the gripper, but for you, the IT guys, you are more on the programming, probably. How to program the robot. For us, it's more on the design on top of programming. So it's very interesting for our student now to design this gripper, and to what extent, whether they can feel, to what weight they can hold, for example, right? So this is another exercise in the lab that normally we give to design for the end effector of the robot for the different functions actually. Next. These are some what we call it design element that use. Normally we use mechanical grippers. and they have suction cups or vacuum cups. We call, you have to, for example, if you go to a vending machine, for example, a coffee machine, for example, you can see that the arm that grip the cups, right? So they have either they use the suction or they use the vacuum cups, for example, and the gripper must be designed that so that when they hold the cups, they don't crush the cups, or when they hold the cup, they must fold the cup must be fold. These are very simple design in the coffee maker or in any machine that they use the end in effector or gripper for design. Sometimes there's hooks, sometimes there's scoops to do some fluid action. So these are the configuration of the. You can see how they release the wire, how they grip the wire, how much force to be exert to end effector. And this need a lot of design for that. Okay, next. You can see there, apart from a gripper, as I said, you can attach to the end grip with the tools. So instead of gripper, you can replace with the tools. So for example, tools like spot welding, arc welding, spraying. You can see at the end there, there's a spraying machine there. And then they can rotate, so on. They can use a heating torch. These are basically more on for the industry, in automotive industry. Next. Next. Yeah, some technical hiccups here. So, okay. Have you done this one?
Hello, Prof. We can hear you. Is the signal unstable again? Hello.
A bit more. Bear with me. Another 15 minutes.
We can hear you, Prof. Your voice is unstable. I think the signal become unstable again. Hello. Hello, Prof. We cannot hear you clearly, Prof. Hello.
Okay, we back now.
Yeah. Okay.
Aduh. Ya, Pak Ari.
Yes, Prof. Hello. Yeah, the signal is unstable, Prof. It's not stable.
Yeah, I'm still here. Can you hear me?
Yeah, we can hear you, but clear, Prof, because maybe the signal is not stable again. Maybe
Okay.
some technical issue with the signal, Prof.
Yeah, signal. Yeah. It's okay. I'm okay now. It looks okay.
Yes,
Can we
it looks okay
continue?
now, Prof. Okay, yeah, we can continue.
Okay, I get about more 10-15 minutes to go. I still got a lot slide to do, but I will do it fast. Can back to the last slide that I implemented. Where is our controller?
Can you repeat again the instruction, Sean? I cannot hear the voice clear.
Can we go back to the slide?
Which one?
Ah, okay.
This one, yeah?
Hello?
Yeah.
Yeah.
These are some of design. As you said again, these are important things. These are some of the design of the gripper or the tool that we use in industry. Okay, so you can see that how the gripper, how it's like a hand of finger. I sign they attach a tool. This is for spraying, and this is for painting, for welding. So the end gripper will determine what are the function of each particular robots. For any robot, like you can see the other the operation, that kind of robot, like in humanoid robots, right? The end gripper. These are the design of the grippers and the tools that use. Okay, quickly next. These are some design in grippers. They have grippers. They have intangible fingers. You can see in the design. They can change the fingers. They have sensor in their fingers. They have multi-gripper, similar like human being. So they are trying to emulate the human figure actually. So standard gripper produced to remove custom design required. That's why I said we need to do our own design for our own application. But basically they try to design like our own human figures, this end gripper. Okay, next. Quickly, as I said, these are some figures. You can see that the application, as I said earlier, even though the Japanese come into the industrial robot quite late, in the world now, you can see the most used robot in the world now is in Japan. Even though the Germany, the one who introduced this industry 4.0, but the application of robot largely are in Japan. You can see in the world there, even surprising also in Singapore is quite a big number there, and South Korea. And in the West, you can see Germany, Sweden, Italy, Finland, even US also. You can see it's quite way back compared to the Japanese. Okay, and our part of the world is not registered there. Other part of the world, include Malaysia, we are not. We are there, but the number is not there. Okay, these are some application more in material handling, processing, assembly, execution. As I said, these are some countries that use robot widely in their industry. I mean to say that to be part of the industry 4.0. Next. Okay, these are some, as I said, some application. For example, like the rotational robot just now, they can use in welding. You can see they can rotate the head in the welding. At the end effector there, they attach a tool, which is the welding tool they can attach. So the robot do all the weldings. You can say they are arranged in the work envelope that they can work in the in the restriction area where they work in their own area. So that's why they're spacing the robot according to the workspace, right? So these are, you can see they can do the welding very fast and very accurate. If you compare to human, we are not able to do what the robot do. Then the next one, you see the robot in a pick and place. You know, they can take the pellets, put on the roller there, and they can pick the pellets and they put another there. And these are the stand-alone robots. They just pick and place on the right hand side. On the welding side, they work as a group, okay, for the welding operation. But this one is only stand-alone pick and place robots. Next. Next slide. Okay. These are some configuration how they design the robot. You can see that on the right hand side, this is the programmer standing there, do all the programs on the right hand side. And you can see the robot is use a pick and place robot there. So these are some operation they are doing. They call it the flux core arc welding. So these are configuration how they use the robot for arc welding. It's made like a station. They have a controller. The robot, they have parts there. Okay. Next. Next slide, please. Okay. This again, you can see how they designed to pick up a cup. They show you how to do the welding. They can show you how to do the packaging. These are the example. You can see that a different operation, they use a different kind of robot, as I explained earlier. Depend on the kind of operation they want to use. Depend on whether they want to do linear or rotational. Okay, next. Again, this is another example. They use in a small cell, you use product assembly. Okay. Next. We don't have a break. We continue. Okay. Next. Next one is more on the programming. I'll do it quickly. Robot is a programmable. They can use a pendant. Before that, can you have the one before this? Can I have the slide before this one, please? Slide sebelum ini. Okay. 3 ways to program the robots. First, a lead through program. A work cycle. They have a manipulator to program. Next slide.
Cek.
Halo, Prof.
Hilang.
Ya, saya di sini ya.
Oke.
Okay, a bit more. 10 minutes. I will go through fast. This is about programming. As I said, they use a literal programming. They use as a work cycle that they can move to control. You can see the program. Or you can use a language programming, a textual program. You can program use a language. We call it a robot program language. This is another exercise that normally we use to the student, how they can program the language to the different functions. And the last one is simulation. Instead of they use the actual robot physically, we do the offline. They do some simulation for certain operation. So either literal programming or robot programming itself, or they use simulation. Okay, these are 3 types of industrial robot programs. Next. These are an example. They have a teaching pendant. They can put, they can request the robot to a certain task. Then after that, they conform with the task. Then it becomes a sequence. Okay, so they use the pendant to control, to teach the robot. Because okay. Next. Next slide. Yeah, this is another example. You can see that manually they teach the end effector robot way to do the task. Okay, and they teach the robot way using the pendant what operational to be done. So once they complete the cycle, they put back into the computer. Then the robot will do it straight from that, physically teaching the robot what to do. Okay. And this one doesn't involve any computer programming. They use the pendant, they guide the robot what to do. Then after that, they put back the programming into the robot itself. Next. Of course, they have some advantage there, downtime, logic capability, whatnot. There is some disadvantage, but easy to program. Next, please. These are the second one. They use a proper programming language. These are basic one. They use Fortran, C language, whatnot. You see, this one. These are some example. For example, these are the typical programming of the robot. Ask them to move, ask them to approach. These are examples of the simple programming of the sensor server. So the second one, they use a robot programming language. Next. So these are example how they use robot programming language to instruct the robot to do some function. Because they said from the programming, this allow the following function that lead through programming cannot really accomplish. They mean to say that they will program in such a way that they will use all the what we call it the capability of the robot itself. Okay, then communicate. Another thing, the first one is using tendon. This one that you can communicate with the robot only through with the computer. That means you can program to the computer. They can control the function of the robot using a computer. This is normally done during for industry. They use a computer to control the robot. The first one is to do only 1 or 2 functions. The second one is easy for you to access using a computer to use what they call it a computer to control. That you can reprogram to do whatever function you want the robot to be done. Okay, that we use the robot program. Okay, next. Next slide. Next slide, please. Okay, the third one is the simulation one. You can see that just now how we simulate the robot operation on the computer. Can I have the slide before this, the simulation? The one before this. Okay, this is the third types of programming. We can use the simulation packages, simulation software that to simulate the operation of the robot itself. That means you try to simulate, you try to program it offline. It's not connected with the robot at all. So use the simulation. Once you satisfy with the simulation program, the operation that you need to be done, then only you transfer this simulation into the actual operation. Yes, it's a simulation. You simulate first, ensure that the operation is correct, all the process is done deal, then you transfer this one to the computer, either using a program language or you use teaching pendant. So you simulate offline first. So these are the three again. Either use teaching pendant, or you use computer programming, or use simulation. This is how we normally design robots. Next. So I will go quickly. The selection of robots depends on a certain criteria. As I said, certain robots have certain function. Next slide, please. So when we want to select a robot, as I said earlier, it depends on the function. How big is the object? What are the operation? Is it just place? Is it just to do some manufacturing processes? And how fast is the robot can move? That's why when we determine the classification of the robot, we can see the speed of the robot. Like the Cartesian robot is very fast, they can move X and Y. The rotation also is very fast. But if you the gantry is big, so the speed is slow. But again, the selection of the robot depends on the process that you want to be. What kind of the productivity you want to be. The payload, as I said, one of them, how big, the speed, how fast, and the working envelope, how big the area that the robot can reach the product, can reach the component. Next. Okay, the last aspect of the robot that I want to touch is more of the safety. So for in any application of robot, whether in industry or at home, whatever, so first thing you must bear in mind the safety, because once you program the robot, it cannot be stopped. You can do the repetitive work. Nobody can intervene their operation. For example, one you set for the welding, for example, or for the spraying, for example, right? There must no human intervention during the operation. So the area must be guarded properly. People can come in. That's why for any operation that in the robot, they have two signals, the red and the green signal. That means the green signal meant to say that the operation is on. The operation is stopped. Okay, so that's why when we're talking about the working envelope, so that these are the area the robot arm can reach. So no human being must be in the area of the working envelope, just to prevent any accident or injury to the people. So you must ensure that for any industrial robot application, they must ensure that the safety comes first, right? And then secondly, about as I mentioned here, a robot can cause accident. A robot can place individual in the last circumstances. You need some mechanical parts fail, for example. if there's some failure there, right? Then the power supply to robot are uncontrolled. So it's all things that you must take into consideration, all this factor when we implement industrial robot. Apart from the advantage that they have, but bear in mind that the safety is important. Because, for example, if the robot can lift 10,000 kilogram work, and we are human beings, maximum is about 90 kilograms. So you can feel the effect if the robot accidentally hit or what we call it, can accidentally with the human being. So another aspect of robot or industrial robot is their safety. And of course, the next one is maintenance. You got to properly maintain so that during the operation, the working time will be not disturbed. I mean, the robot can do the maintenance, the programming. These are the safety aspect of industrial robots. Okay, next. So with proper control, you can injure. This is most importantly, you can injure to the human workers actually. These are some safety implementation procedure. I can just brief quickly. The human interaction, authorized access, and probably during the operation there's some mechanical failure. Somehow the joint or the inflector doesn't work. And the power system sometimes, under operation, there must be some power supply problem, things like that. And again, if improper installation of the robot, it can cause a danger, hazard to the user. So you need an expert actually. You can look at the diagram there, how important is the safety. Next. Okay, you can see there how they implement the safety aspect. They put all the fencings around the operation so that people can go intervene. Okay, they put some barriers, some fences around the robot, so that probably if there's no mechanical failure, people can go in. For example, like in the welding, people can move in while the welding is operation. And you can see the last one. You can see how the put around the operation of the gripper there. These are some safeguarding method to ensure that for the safety of the worker in the factory. Next. As I said, they put emergency stop. If anything happen, they have emergency stop there, interlocking device, so that they can stop the operation quickly on the guard. If somebody access to the fence, they automatically stop the operation. They cut off the operation. Next. Almost there. Next. These are some example again. They even have some sensor to prevent people come in and interrupt, right? They show you some safety switch for that. Okay, next. The position of the switch of the maintenance. So any interruption, the switch we quickly activate so the operation can be stopped. Next. Okay, this is an example of device. Then to say that while the robot in operation, we still can control it manually. Okay, it's as you just press on or off, for example. So if the operation is ongoing, you let it on. You want to off it, you can just press the yellow button. It just stop. This is another devices for the safety. Next. This is another one. It's the full system of the robot. You can see that the assembly there. You can see the full system of the robot. how they use the safety system. So for any operation, you can see how they use the fencing, how they use in the red one. You see they have interlocking signal. You can use a stop button there on the right hand side. So these are only the safety area of the working envelope of the robot. Okay. It's a secure area for the robot to work with. Next. These are some safety standard to be followed. So meaning to say that for any application, you must follow these are the safety standard, or else the operation cannot be secure. So these are, you must follow, these are the standards that you use in Europe and North America for the safety reason. You must have this standard before you can operate the robot itself. Okay, these are an example. Next. Next, okay. These are some economic justification. There's some calculation because, as I said earlier, to buy a robot is not expensive. Remember from my earlier slide, the Industry 4.0, one of the challenges is a very high capital, because to buy any equipment or any devices for Industry 4.0, apart from robots, for another item like in the enabler, are very expensive. So we have to justify why we need the robot in that system. So this is where normally the accountants will come in. Why must we have the robot? What are the return of the one, so that they can put the investment to buy the robot. It's not cheap for the robots, but again, they have to be justified. The rate of returns for the company. These are some economic justification, right? You can you use a formula for that. Next. Okay, this is my last part of the presentation. Apart from the industrial robots, there are other types of robots that are in the market now that we can see. As I said, whatever other type of robot, they have the same configuration, the same function as industrial robots in terms of the gripper, in terms of the joints, in terms of their programming, but they might have different function from the industry. Okay, these are other types of robot that we can find in the market now. Next. We can find robots in entertainment and leisure, leisure industries. I think you have to see how this the dog, the eyeball, playing with the children, the iRobot. You can see if you like Transformer, you know Transformer. If you like Transformer, this is part of entertainment. How they can change the car into the robot, and the robot can speak. That is another application of robot. But still the same. You can see on the car. These are all same basic. They can change. They can be programmed. They can change whatever. They are in the entertainment industry, even in the leisure. Next. There's some robot to Mars in 203 because they're not ensure the environment in the Mars, whether it's the environment is safe for human or not. They send the robot to the Mars to take some sample, you know, to look how the environment there. And as I said, they can move, they can rotate. So this is another application in the space robots. The NASA now, the US, the NASA now is using and still developing robots to use in space now. Okay, robot in space. Next. Remember they call RB2. You look the Star Wars, you know. RB2. You see, there are human. They call it human robot joint crew in the space station. They even want to send a human-like. They call it a human-like robot. They call it humanoid instead of human to be sent in the space station. This is still space robot. Okay. Next. Some is used for some research purposes, like Honda. You can see Asimo. These are very, very famous Asimo robots. They can use some marketing, you know. They can use some introduction to production. Because Asimo, I visited Honda factory a few years back. They use even a robot to welcome you. Asimo can use most things that can help you. So they can help you. It's like a human, but again, this depends on our programming, how they can help us. This is where sometimes in modern life that we need some robot to help us in the more day-to-day application, home and domestic application. See, so these are some research robots that be done. An example is you can see the Asimo there. Next. We do have now, we call it underwater robots, to control vehicles that trusted for maneuvering and robot arms for grabbing, where to go certain depth of the water that human cannot stand the pressure. They send a robot to that, and particularly they use it in oil industries, where they drill the platform down deep sea, so only machine can stand the pressure. So they use underwater robots, some exploration purposes to explore, to find that whether the area have some, oil production, things like that. For example, here they call it robot tuna, used for oil exploration. You can find it on the YouTube how they use that. And these are some application robot underwater, and this can be designed. Okay, robot underwater. Next. Again, interestingly that we use medical robots, because remember in the beginning, robots can do a very accuracy operation. First, secondly, they can they don't have things like tiring and fatigues. Some major operation, it takes sometimes more than 2 to 3 hours. Okay, so only robot can do this operation because it's very long time. So they can use robot for surgical purposes, for example. Can you use this? They can use a But surgical, they use in prosthetics, for example. Remember that industry accident occurs sometimes. Some people lose their legs, use their hands, but they can use prosthetic hands, for example, to help the workers back. For normally, sometimes in industry accident, they use robot to help for rehabilitation, right? They use robot to help people to gain back their walking.
Hello, Prof. The signal is lost again. Hello.
Okay. So again, surgical, they see, then
Yeah, the signal is not stable, Prof. There are the technical issue.
Apa dia, Pak?
Nya tidak stabil, Prof.
Okay, one more slide, two more slide. Next.
Okay.
Okay, now okay. This is more interesting. They call it nano robots. They can even send devices, or we call devices, or robot, we call it, into the bloodstream to do some operation, to diagnose some patient. See, they can send the robot through the bloodstream. You can see that. These are the research being done in medical robots now. They could will be used in patient bloodstream to show illness. That means probably we doesn't not a physical operation now. They can what they call it, install the robot into your bloodstream. They can find out where your lung been blocked, where we need some they can remove probably some what you call it, a plug in your bloodstream. You know, for those who have some heart problems, they can send a small devices. Well, you can call it tiny robots to go into our bloodstream, and these are the future. This is another thing that are the future of the application. Another thing you can, the military, for example, they can see unmanned aerial vehicle. Okay, they can send for thousands of miles to send the rockets, you know, unmanned. This is part of the robot. See, and
hello, check.
okay, Ari. So these are the. Can you hear me?
Yes, Prof. We can hear you
Ari?
clearly. Okay.
Can you hear me?
Yes. Yes.
Okay. So these are the future medical robots. Yeah, we call it nano robots. Okay, next. Okay, that was my last slide of the other robot types that we use apart from industry. They use in underwater, they use it for medical, they use even for the entertainment. And I not to mention here that they use some robots in military application, for example. That's very quite sensitive. They use robot for military. And now, before I end my presentation, before the Q&A session, I have two videos to show you. The first video is a small scale of how they integrate the manufacturing system that to produce a certain product. And this is not a different component to be integrated. As what in Industry 4.0, we're talking about integration, we're talking about data, we're talking about collaboration. Okay, that's the first video that I want to show. The second one is the application of industrial robot especially in automotive industry. So what I have explained from the beginning, from Industry 4.0 to the application, you can see the actual action of robots in industry. So I will request Ari to play the first video first, then the second one, the automotive video. Okay, please Ari, share us the video.
Industry 4.0, a synonym for the production of the future, a production which can be adjusted quickly and flexibly to changed market requirements, and which makes economical production of customer individual products in smallest quantities possible. This is ensured through the implementation of state-of-the-art information and communication technologies and their networking in the Internet of Things, of services, of the production processes. He outlines strategies, evaluates optimization potentials, and intervenes if necessary. He is supported by innovative human technology systems, which support him especially during highly complex and non-predictable activities.
For already 10 years, the Smart Factory is the pioneer of the intelligent factory of tomorrow. As a competence center and manufacturer-independent demonstration and research platform, the Smart Factory develops innovative factory systems in which the vision of Industry 4.0 has already become reality.
In a network of renowned partners from industry and research, we are working on new concepts, standards, and solutions which form the basis for a highly flexible automation technology. In 2014, we presented the world's first manufacturer-overreaching Industry 4.0 plant in a modular design in a consortium of selected partners. The basis of any Industry 4.0 realization are consistent interfaces. Besides mechanical standards, electromechanical and information technological interfaces, such as uniform plug connections or communications protocols, are especially relevant. The manufacturer-independent plant produces an intelligent product, which controls its own production by means of an RFID tag and transmits its individual configuration to the different modules. This efficiently ensures production down to batch size 1. The smooth and quick transfer of all relevant data is possible due to industrial Ethernet from the backbone of the plant, modular infrastructure. Thus, a continuous and transparent information flow in real time is ensured. A scenario illustrates the relevance of the cross-system data transfer and evaluation. The modules integrated into the plant are recognized automatically, and the current status is continuously transferred to the integrated IT systems. If the status of the module is marked as faulty, the worker receives an automatically generated message on his mobile device. The modular structure ensures a simple and quick decommissioning of the according production unit. After the module has logged off and its gates are closed, the worker can remove the unit from the process. To bridge the gap, a bridge module is integrated into the production process. The workpieces removed out of the bridge module continue to be produced at the manual workstation, parallel to the maintenance tasks. Marketable solutions train or accompany the employee during the execution of the production step to be bridged. Parallel to manual production, the defective unit is being replaced. The maintenance and repair work is made easier for the worker by means of augmented reality. Smart glasses are used for instruction and support by overlaying what was seen with according recommendations for action. As soon as the repair tasks have been completed, the bridge module is replaced by the repaired cell again. The monitoring system recognizes that the module is available again and contains the current data. At the same time, the engineering automatically provides the suitable parameters to integrate the changed module into the process for quick and easy configuration. The production is completely taken over again by the plant. Our members and sponsors create a lively partnership to realize the vision of the factory of tomorrow. If you want to help create the future, we invite you to participate in this strong network. The Smart Factory offers you the suitable platform for this.
Okay, from that video, you can see all the element of Industry 4.0 is being shown in that small video just now. It's all implemented, the IT, the robotics, the integration, the programming, and the cooperation. You see, there's so many companies are participating in this smart factory. So we need that collaboration. You cannot work alone. So all the element of the Industry 4.0 is being shown in that video just now, as what I had told you earlier, right? So the next one, let me see on the application in industry, especially in the automotive industry, how they really use extensively in the next piece. Yeah, the next video.
Welcome to BMW Production, Jensen. I'm pleased to show you why BMW sets the standards for innovation and flexibility. Our collaboration with NVIDIA Omniverse and NVIDIA AI leads into a new era of digitalization of automobile production.
Fantastic to be with you, Milan. I'm excited to do this virtual factory visit with you.
We are inside the digital twin of BMW's assembly system, powered by Omniverse. For the first time, we are able to have our entire factory in simulation. Global teams can collaborate using different software packages like Revit, CATIA, or point clouds to design and plan the factory in real-time 3D. The capability to operate in a perfect simulation revolutionizes BMW's planning processes.
Are those gaskets still in the right place for you?
Yeah. BMW regularly reconfigures its factories to accommodate new vehicle launches. Here we see two planning experts located in different parts of the world, testing a new line design in Omniverse. One of them wormholes into an assembly simulation with a motion capture suit, records task movements, while the other expert adjusts the line design in real time. They work together to optimize the line as well as worker ergonomics and safety.
Can you tell how far I have to bend down there?
So we'll get you a taller one, but there's...
Yeah, it's perfect.
We would like to be able to do this at scale in simulation.
That's exactly why NVIDIA has Digital Human for simulation. Digital humans are trained with data from real associates. You could then use digital humans in simulation to test new workflows for worker ergonomics and efficiency. Now your factories employ 57,000 people that share workspace with many robots designed to make their jobs easier. Let's talk about them.
You're right, Jensen. Robots are crucial for a modern production system. With NVIDIA Isaac Robotics platform, BMW is deploying a fleet of intelligent robots for logistics to improve the material flow in our production. This agility is necessary since we produce 2.5 million vehicles per year. 99% of them are custom.
Synthetic data generation and domain randomization available in Isaac are key to bootstrapping machine learning. Isaac Sim generates millions of synthetic images and vary the environment to teach the robots. Domain randomization can generate an infinite permutation of photorealistic objects, textures, orientations, and lighting conditions. It is ideal for generating ground truth, whether for detection, segmentation, or depth perception. Let me show you an example of how we can combine it all to operate your factory. With NVIDIA's Fleet Command, your associates can securely orchestrate robots and other devices in the factory from mission control. They can monitor in real time complex manufacturing cells, update software over the air, launch robot missions, and teleoperate. When a robot needs a helping hand, an alert can be sent to mission control, and one of your associates can take control to help the robot. We're in the digital twin of one of your factories. but you have 30 others spread across 15 countries. The scale of BMW production is impressive, Milan.
Indeed, Jensen, the scale and complexity of our production network requires BMW to constantly innovate. I'm happy about the tight collaboration between our two companies. NVIDIA Omniverse and NVIDIA AI give us the chance to simulate all 31 factories in our production network. These new innovations will reduce the planning times, improve flexibility and precision, and at the end, produce 30% more efficient planning processes.
Milan, I could not be more proud of the innovations that our collaboration is bringing to the factories of the future. I appreciate you hosting me for a virtual visit of the digital twin of your BMW production. It is a work of art.
Dengar Ari?
Yes, Prof. Hello. Hello, Prof. Okay. Hello. Yeah.
Halo.
Okay. Yeah.
Alright. Tadi ada yang the last two videos, ada yang saya tunjukkan. Yang pertama tadi ialah a small teaching at the factory of the future, where they use a very full integration of what we're talking about, the industry 4.0. The second one is the actual action in the industry, the BMW, the extent of this integration, AI, robotics, digital, everything is there. From these two examples, we can summarize that what I have explained to you on the IR in the industry 4.0, the robotics, and how the importance of the robotics in the manufacturing industry especially. But then again, it's not only in industrial robotics, but again, I did show briefly on the other application now in entertainment and in medical. For the IT student, I think for me, it's more important for you to look into the design and the programming and the other application for industry. Because if you are an engineer, as I said earlier, because I'm an engineer myself, you are more on the design of the robot itself. For the IT, they must be focused on the programming, on the AI, on the digital, on the augmented, things like that. I think the IT has to be integrated into the engineering, because without the IT is an enabler also and engineering. We cannot do our teaching, our factory of the future without the IT to come in. So I did advise for some of our students that you must understand some of the manufacturing activities, see, because most of 70% of industrial robot, they are used in industry, apart from other application, entertainment, you know, medical, things like that. So it's nice for you to have one courses on the manufacturing processes, so that you can understand where to apply the industrial robot. At the same time, being an IT student, you must know about this AI, for example, artificial intelligence, how the human part of it, how they use in prosthetic, for example, how they design, you know, all these games, things like that. So actually, this lecture I can give in more 2 sessions, actually 4 hours, but since the time limit, I tried to condense it between 2 hours. And I know that there's some we call it interruption of the nature of the on the line. I hopefully the student can grab some of the important element that I've been shared in the lecture. It's much better if we can have face-to-face lecture, so that we can interact more easily, more understand. But anyway, it's not a big problem. Ari and Eri, you can share my presentation to all students so that they can look back on the notes. They can look back on the notes and as their reference, for example. Inshallah, if there's sometimes, if I'll be there, I'll come and visit you. But again, before I close the session, if there any question from the student or any lecturer that we can share, is any question that you like to ask me, please.
Okay, thank you very much, Professor Dr. Abu bin Abdullah, for the information and knowledge which have been given to us. Well, even though there are some minor issues on signal problems and technical issues, I'm sure that it doesn't hinder our willingness to learn, and may it be very useful for us. And sure is the material that Professor Abu shared for knowledge, especially in the field of robotic in industry 4.0. Okay, ladies and gentlemen, now we move to the next agenda, which is question and answer session. Well, for the audience who wants to ask the question, you can just use the raise hand feature and open your camera, mention your name and state your question. Or for the audience who have signal issues or technical issues with the connection, you can use the chat feature at the side of the screen, state your name and state your question. Okay, we begin our question and answer session. Who is the first questioner? Who is the first contestant to ask the question? Please raise. Mas Restu Akil. Please open your camera and now state your question. Okay.
Is my voice clear?
Yeah.
Yes, very clear. Okay.
Okay. Thanks in advance, sir. Before I ask a question, let me introduce myself. My name is Restu Agil Arjun from Unisa Yogyakarta, batch 2021. Student ID number 211501027. Let's get started. I was graduated at vocational high school, especially in mechanical engineering. And I also learned about CNC machine with Cartesian coordinates around 2 years ago. There is X, Y, and Z. Simple question, sir. That means CNC machine is one of the technologies of Industry 4.0. Is that true, sir?
Thank you, Agil, for your information. CNC is my specialization, actually. CNC has been there for some time, you see. But again, in the beginning, if you look about 30, 40 years back, because of the absence of the computer, the CNC, they use a punch card, they use a tape for the programming. If you study the history of CNC, first they call NC, numerical control. They use a numerical 1010 to control the machine. Then come in the late 50s or 60s, when the computer come in, they use computer to control computer, okay. And since then, there are different type of operation that CNC can do. They can do the drilling. Since you're a medical student, you understand me. They can do the drilling. They can do the milling. These are all operations that can be do. Correct. You can see in the video just now, they use the robots to what you call it, to put the components into the CNC machine, because CNC machine is a production machine. They produce things, right?
Right.
So, CNC machine, they can work alone by itself. But it's more productively if the CNC machine you arrange in a very cell. We call it FMS, Flexible Manufacturing System, or CIM. They call Computer Integrated Manufacturing System. So they integrate the CNC machines. They use the robot to load and unload the product, right? They use CNC machine sometimes to be part of the whole processes. So the question is that is CNC is part of Industry 4.0, right? Yes, there are anything that use data, use computer control, that can be connected, they can be integrated into the system. They are Industry 4.0. But again, now in the CNC system now, there are more axes now, not only X. They can have more 6 or 8 axes now. For example, you want to machine an engine block, for example, right? Probably before that, they have only one operation for one machine. They use the boring, they use the milling. But in one CNC system, right, with all this, what we call it, axis of freedom of axis, they can use the machining in more than 6 or 7 axes. In one CNC machine, they can do several operations now. Okay. I don't know about Indonesia. I think there could be some industry there, many industry there using CNC, depend on application. But most of the CNC be used in, as I said, in either in automotive or in aerospace. Because in aerospace, they need a very complicated part and very high precision. Same as in automotive. They same in electrical also. So they call it NC is the mother of all machine. So without CNC, the production can go ahead. So as I said, this is my topic, CNC. But again, thank you for the question. This is part of industry. Even though the robot, as I said alone, the robot has been there since in the 30s. But since the development with the technology, now they improve the robots. Okay, so to make it as a system, the robots, the CNC, the digital, the AR, they become a complete system of factory of the future, they call it. That's what you see in the video just now. Okay?
I got it. Thank you. Thank you.
So I think you should go. It's in your mechanical, you can understand robot is much more easier.
Thank you.
Yeah.
Okay, Agil?
Okay.
Yes.
Thank you.
Thank you.
Thank you. And thank you, Prof, for the answer. I will move to the question chat feature. Well, there are lots of questions, sir. I do hope that we can answer all of this question because, well, the time is limited. But okay, I will move to the question from Muhammad Ihza Putra Handayani from one of the students from Information Technology. Excuse me, Prof, I want to ask the question. In your opinion, is there any chances that we go from Industry 4.0 to 5.0? And if there is a change, what is Industry 5.0 will be? Or instead, there are also many chances that we will back again, or we will go downward to the Industry 3.0. In my opinion, as we can see that in our era, especially in the developing country, negara berkembang maybe, there is a way to the technology is beyond their imagination, or in Indonesia we canggih for us to change the era of Industry 4.0 to 5.0. Maybe there is the question is, what is your opinion, sir? Okay, thank you very much. That's the question, Prof.
Yeah, a good question. Because now we live in the world of technology, the world of digital, the world of interconnection. For example, now, I mean, 4.0 will become obsolete for another 4 or 5 years more. Then I will move to another, probably, as you said, 5.0. For example, look in entertainment, for example, if you see in the film called how they transform from one world to another world. You see, this is where they can communicate through the IT, through the technology. This in entertainment world. But in terms of a military, for example, in military, People don't go to the war anymore. They don't need to go anymore. They just send, you know, SCAD, everything, just got bus computer. And then example, for example, in our living, right? Now we are in the process of car now. The car with driver, for example, you know. Even in Malaysia now, we are now almost have autonomous car. We can have a car now, which can park by itself. So for the ladies, it's difficult to park. So they have autonomous car now. So for me, with the power of the technology, the power of the computer now, you can see many things that can be done. You see in medical, they can have these small nano robots to put in your bloodstream, right? You don't need to go for hospital, for example. In military, they simulate like what you call it, or like a flower. They can send it for. So imagine beyond your imagination, what. So, but it's depends on us now. How fast can we catch up with this industry 4.0, industry 5.0? As I said, what are the challenges that we have now? Okay, first is the economy. It's not that cheap. Secondly, is the government. Are they willing to spend money to help us? Like people in industry, for example, I'll give you an example. The Japanese, the Korean, and the Taiwan. These are the three competitors. Okay, the China come later part of the world. Now, how come the China come in now? The technology of the China now. You look at the South Korea. The best, you know, communication company is Samsung in South Korea. You see, so these are the things. Now they have what you call it outer space holiday, or what do you call it? I don't know, they send people for holiday in outer space, for example. So these are the things that sometimes we cannot imagine. Probably not during our time, probably other generations. We cannot imagine how fast the technology is changing. Same with the industry, same with on the security, same with the government. Now people don't go to the banks anymore. I don't know about Indonesia. People don't go to the bank. You got to go to the bank, just probably want to check the book. See? Now this is you see, this is my Note 10 Plus. I have my 10 thesis inside here. I can read. I can on my car with this one. So this is you know, beyond imagination. With this piece of a lot of things can be done. So especially for the IT student, I said again, you start to imagine, you know. Yeah, the concept is there, but how can we explore? The challenges, as I said, the economy, the support, the understanding, and the skill. You need a certain skill to explore this possibility. For me, sky is the limit for you to explore for the industry 4.0. Even that industry 4.0 was introduced a very beginning of 2010, almost 15 years already. Now people talking about industry 4.0, but in Japan also they have launched for the society 5.0. They call it in Japan. They call it society 5.0. We can Google up society 5.0. How they change the mentality of the society. Those who are born in those who are now in 60s or 70s, they cannot be bothered about this technology. But the young generation, you see, you cannot live without handphone. You cannot live without computer. You need to be connected now. So, who are the to come, as I said, to think how can we make, you know, more interested for our community. No, there's no limit. With the power of computer, I tell you, many things can be done. Okay. Good question.
Yeah. Okay, thank you, Prof, for the answer. There is always a chance for advancement. Yeah, Prof. But how we can catch up the technology advancement and how we come up with a solution for this. I think it depends on our generation to overcome the challenge. Okay, next, since this is there is no one that raising the hand, or there is no one that raise a hand, I will move to next question. Mas Naval Audi.
Yeah.
This is the question. I would like to ask you something, Prof. The question is, how does a robot work for the big data industry? And what are frequently applied robot type in the 4.0 era? Okay, I think this is the question from Naval Audi. Okay, thank you very much, Prof.
I can get the question right. Is what type of the robot that apply for the industry? Is it, or can you refresh me the question?
Okay, the question is, how does a robot work for the big data industry, and what are frequently applied robot type in the 4.0 era?
Okay. As I said earlier, I mean, not all robots can apply in all situations. Like, remember when the end gripper, either the gripper or the tools. Normally, the gripper is used in certain industry. The tools is used more in the manufacturing industries. For example, in bottling, for example, it's just simple robots, just a gantry, just pick up the bottle, close the bottle, pick and place. It depends on the type of industry that you're in. What I showed you just now is more on the in the automotive, because I'm more involved in automotive and aerospace industry. See, because we're talking about precision. As I said, that's why they have 5 different of robots to go 5 different function. The Cartesian, the polar, these are all depends. If you look back at the data that I showed just now, the world application of the robots, you can see that you refer back to the data. And these are the different kind of robots they've been used: the material handling, and the packaging, and the what we call the welding, spraying. And you refer back to that slide that show you roughly what are the applications in the industry. So they give you some figure out. I cannot say the SCARA or the Cartesian or the Polar is more used than on that, but depend on the industry, depend on the operation, depend on your products. See, so go back and refer to that slide. You can see which are the robots, type of robot being mostly applied. And that is my answer. Go back to that slide.
Okay, thank you very much, Prof.
Yeah.
We move to the next question from Miss Rovalia Adela. This is an interesting topic, I think. This is, as we know that many robots were produced in the industrial 4.0 era, and it is very likely that the industrial era will be more advanced. Even now, the development of robotics has grown rapidly right now. Okay, the question is, what should we do about the robots that have been replaced, and are there any institutions or places that process robotic parts that are no longer used? Because, well, robotic will definitely cause new problems if doesn't treat it correctly. So this is about the how to use the part that replaced, or how we maintain the robotic waste. Thank you. Okay, this is the interesting topic, I think, Prof. Okay.
As you know, for any what they call it, any equipment or for any machine, what we call it, they have the lifespan. Okay, and the lifespan of each, for example, the question is in the robot. The robot, as I said earlier, on the maintenance, how you can maintain the robot to be in optimum condition, right? Sometimes when the robot have come to their just end of life, the robot has been replaced. But depend, as I said earlier, some industry, they design their own robots. Their own, right? So this is, if they don't use the robot, for example, they can depend on the, as I said, it can depend on the industry itself. Either they can remodify or re-engineer again, because the cost of the robot is expensive, to buy, quite very expensive. So economically, they must justify. The robot has to work 24 hours around the clock to produce a certain return, the net return of the company. So for them to maintain the operation very optimum, they have to maintain the maintenance. But once they reach end of the life, right, they can be replaced by another robot. Either that robot can be repaired, can be used something else, depend on the industry. But again, as I said, the end gripper and the grip, that is the most important thing. So the lifespan or the application of the robot depends the maintenance. Secondly, at the end of the operation, you can modify the robot. Can you put something else? See, you can see how, in the factory, if you can use the robot, you just use it. But if you cannot use it, you repair it, you improvise it, you change it for some other purposes. For a robot, for any things that they have certain lifespan, they can spend more effectively. If they cannot do the function as what they want it to be, so we just change to other function. Or probably the last thing that you can do is just sell it as as the scrap material. That's what we can do, right? So depend on us how we maintain, how we use the robots. You can use for something others.
Okay. So the how to use is depend on the person who what is it, the robot also, depend on us how do we maintain the robotic waste so that doesn't cause any other problems.
Yeah,
I think, and I think this is the last person. There is a lot of question asked, but the time is up. So I'm so sorry that this will be the last question from our students, and maybe the next questions will will be discussed in other time, and maybe we can do some more collaboration on workshop on robotics or on maybe robotic programs. This is the end of the question and answer session, and thank you for the audience that had participated actively. There is a very, very interesting and outstanding discussion session. Okay. And thank you for the answers and very, very outstanding answer, Prof. Abu bin Abdullah. Okay, now before we reach the final session of our webinar, for all of the audience, please open your cam and we will do the photo. This photo session will be handled by Mr. Sadr Lufti Mufreni. For Mr. Mufreni, okay, the time is yours.
I think not all of them already open the camera.
Okay, come on.
Okay, open your cam, please.
Wait a minute, 5 minutes, Mr. Sadr.
Okay, no problem.
maybe prepare.
Yeah, okay. Maybe the students are preparing something before we do the on cam.
Do you use online or face-to-face teaching now, Ari?
Yes, Prof.
Hybrid, Prof.
Hello.
Hybrid.
Yeah, we do in hybrid session, Prof. Yeah, sometimes they do offline, and well, some other sessions are doing in online.
Yeah. our next session in Malaysia, we start next week. So I think about 50% they will allow to go back to the university.
Oh,
Okay. Yeah, I think in Unisa it will be the same, Prof. But this is right now is still 70% online and 30% offline, because some issues is not solved yet. Okay, everyone.
Inshallah, we hope we're back to normal soon.
Yeah, hopefully we're back to normal soon. It's been almost 2 years, Prof. We're doing online.
Yeah.
Amin.
Okay, Mr. Sadr, maybe you can do.
Now, yeah.
Okay.
1, 2, 3. Okay, one picture. Let's see goes again. 1, 2, 3. Okay, one more time. Okay, thank you very much.
Okay, thank you very much, Mr. Sadr. Well, finally,